Imagine you're an expert driver, right? You spent your entire life mastering the road, the clutch, the steering wheel.
Yeah.
You know exactly how a car handles around tight corners.
You're totally in your element.
Exactly. But today, you are suddenly asked to fly a spaceship. And I mean, suddenly those driving skills, they won't help you much here at all. In fact, you're basically starting from square zero.
Oh, yeah. It's the ultimate fish out of water scenario because the physics of the universe haven't changed, but your entire method of navigating it has been completely upended. Like, you can't just press the gas pedal in a vacuum, you know?
Right. And that spaceship analogy that comes straight from Charles Scalfani's writings, and it just perfectly describes what it feels like to approach functional programming after a lifetime of, well, imperative programming.
It really does. It's a huge shock to the system.
It is. So our mission today for this deep dive is to help you bridge that massive mental gap. We're unpacking the Class 24 notes for your CS330 programming languages course, and we're looking alongside the assigned readings from Scalfani and Janet A. Carr.
Which are fantastic readings, by the way.
Really good stuff. But to be clear, we are focusing entirely on the mindset shift today. We're going to skip the specific syntax of languages like Lisp or Clojure for now.
Yeah, I mean, there will be plenty of time to drown in all those parentheses later on.
Exactly. So many parentheses. But today is just about rewiring how you think about logic itself so you're totally prepped for your upcoming class and labs.
So to understand how to fly the spaceship, you first really have to unlearn how the car works.
Unlearn the car.
Right. And that requires looking at the fundamental difference in philosophies between imperative and functional programming. I mean, imperative programming, so the C, the Java, the Python that you're probably super used to, it's obsessed with hardware architecture. It's completely chained to the von Neumann model.
And that model, just as a refresher, it essentially treats the computer like a giant warehouse, right?
Yeah.
With a very specific mechanical assembly line.
Yeah, exactly. You're constantly having to think about the machine's memory. You pulled data out of a specific memory address, put it on your workbench, physically change it, and then shove it right back into that exact same slot on the shelf.
You're manually tracking the state of your variables as your program runs line by line. It's micromanagement.
Total micromanagement. You're giving the computer these agonizing step-by-step instructions on exactly how to do every little thing.
Right.
But functional programming, it shifts the focus entirely away from the hardware and those step-by-step state changes. Instead of micromanaging the machine, you are just declaring what the final mathematical result should be.
Which is wild.
Yeah.
And I noticed the material really leans heavily into this idea of mathematical expressions. That feels like a massive leap from hardware manipulation.
It is. But think about the foundation of mathematics, right? It's all about proof. If you can express your program as pure mathematical functions, you can, theoretically anyway, mathematically prove that the code operates correctly.
Because there's no hidden state lurking in the background of your system to, like, mess up your proof.
Exactly. If you write a mathematical function, it just takes an input and produces an output. It doesn't secretly change a global variable halfway through its run.
Which is a lifesaver. And John Bacchus, he actually hammered this point home during his 1977 ACM Turing Award lecture.
Oh, yeah. Bacchus is a legend.
Right. He's a giant in computer science. He's the B in BNF, the Bacchus-Now form, which, we've all wrestled with in syntax parsing.
Oh, you all had the scars from that.
Seriously. But he used his Turing Award platform to put this massive spotlight on functional programming. He argued that because functional languages lack state, their operation is completely predictable.
And predictability leads straight to provability, which gives you vastly more reliable software.
But the timing of Bacchus's lecture is, well, it's a fascinating piece of history to me. Because functional programming isn't some trendy new framework.
Not at all.
The theory has been around for decades, predating a lot of the imperative languages we use today. But it was practically held back for a long time by hardware limitations.
Right, that von Neumann bottleneck we mentioned earlier.
Exactly. Because functional languages, they abstract away all that direct memory management, and early computers just couldn't run them efficiently.
No, they were agonizingly slow compared to a highly optimized C program where, the developer was literally manually managing every single byte of memory.
Yeah.
It wasn't until Moore's law really accelerated, processors became exponentially faster and memory became vastly cheaper, that the industry could actually afford to prioritize this mathematical readability over raw, bare metal hardware efficiency.
So the hardware finally caught up to the theory.
Yeah, basically. Yeah.
But okay, if we're adopting that mathematical theory, we have to break some deeply ingrained habits. Like if we're relying entirely on mathematical proof, that completely shatters the first tool every single one of us learned on day one of coding.
The variable.
The variable. Scalfani addresses this in a super blunt way. He points out that in any basic algebra class, the equation x plus 1 makes absolutely no sense.
Right. It's a logical impossibility. Nothing can equal itself plus 1.
Exactly. But in imperative programming, it's literally the most normal idiom in the world. You take the value of x, you increment it, and you store it right back in x.
Yeah, we do it 100 times a day. But he drops a pretty shocking statement in his article. In functional programming, x equals x plus 1 is completely illegal.
Totally illegal.
Yeah. In functional programming, stored values are still called variables, just due to historical convention, but they are actually constants. Once a value is assigned to a name, it never, ever changes for its entire lifetime. It is strictly immutable.
And the class slides call this referential transparency, meaning you evaluate an expression, and you can replace that expression with its result without changing the program's behavior at all.
Because it's completely locked in.
Right, but I have to push back here because this is exactly where my brain completely stalled out reading this material.
It's a common roadblock, yeah.
Like, if absolutely nothing can change, how do you build a working application? Think about a simple while loop. You need a counter variable updating, right? Like I plus b. If I can't mutate, how does the loop ever terminate? The spaceship just crashes straight into a sun.
You're reaching for the steering wheel again.
I am. I can't help it.
But the spaceship doesn't have a steering wheel. In a strictly functional language, you actually don't use traditional loops at all.
Wait, really? No loops?
Hope. Loops inherently require a mutating state to eventually trigger an exit condition. So instead of loops, you use recursion.
Okay, so the function just calls itself.
It calls itself, yes, but, and this is the key, it passes new parameters forward.
Oh.
Let's say you want to count down from 10. In C, you'd make a variable, set it to 10, and then mutate it down to 0. But in functional programming, you write a function that takes the number 10. It does its work, and then it calls itself, but this time it passes in a newly generated number, which is 9.
Oh, I see.
Then that instance calls itself with an 8. And this just continues until you hit a base condition like 0, which stops the whole chain.
So instead of mutating a single counter, I'm just constantly generating new values and passing them into fresh function calls.
That is the core mechanism, yeah. And it ties directly into the concept of pure functions. A pure function relies solely on the inputs provided to it.
Okay.
It doesn't read any global state floating around the application, and it doesn't modify anything outside of itself. For a specific input, it will always return the exact same output. 0 side effects.
And the notes actually map this out using terms straight from algebra, which I liked. The domain is the set of allowed inputs, and the range is the set of allowed outputs.
Exactly.
And the mapping from domain to range is absolute. If I pass a 5 into my pure function today, I get a 10. If I pass a 5 in next year, I still get a 10. It doesn't care if, like, the database connection dropped or if another user happens to be logged in.
Right, and think about what that does for testing your code. Testing imperative code often means spending hours mocking up this massive, complicated environment just to see if one tiny function behaves correctly in a very specific state.
It's a nightmare.
It really is. But with pure functions, testing is trivial. You pass an input, you assert the output, you're done.
Janet Acar's reading frames this as a shift toward what she calls transformations over instructions.
I love that phrasing.
It's so clear. If I have a data structure, let's say a list of users, I'm not writing instructions to go in and tweak that exact list.
Yeah.
I pass the list through a pipeline, and I get a brand new list back out. The original list of users stays completely untouched.
Right. If you need a list of active users, you don't iterate through the main database array and just delete the inactive ones. You pass the array to a pure function, and it hands you a brand new array containing only the active ones.
Well, okay, the real world is messy.
Yeah.
Applications have to do things that are inherently impure. We have to print text to a monitor, save records to a database, read keystrokes from a user. Those are all state changes. They're side effects. If our code has to be mathematically pure, how do we actually interact with a user?
Well, functional languages can't eliminate side effects completely, right?
Yeah.
Otherwise, they just heat up the CPU and sit there doing nothing.
Right.
The strategy isn't to pretend side effects don't exist. It's to strictly contain them. You architect your application so that the vast majority of your logic, your calculations, data transformations, business rules is pure, predictable, and mathematical.
So you build this, like, pristine core.
Exactly, a pure
Yeah.
core. And then you push all the messy, impure side effects, the database calls, the UI rendering out to the very edges of your application. You create an impure shell around a pure core.
Oh, that makes total sense.
Yeah. So when the user clicks a button, the impure shell catches that event, hands the raw data into the pure core. The core safely calculates a new state and hands it back out to the shell to be drawn on the screen.
You segregate the chaos. I like that. But inside that pure core, if we don't have variables and we don't have standard loops, I mean, we're missing an entire toolbox. How do we actually construct these complex pipelines?
Well, in functional programming, functions aren't just actions anymore. They become the building materials themselves. They are what we call first-class citizens.
Because in imperative languages, a function is really just a procedure. You jump to a block of code, run it, and return. It's a verb.
Right. But in functional programming, a function is treated as a value, just like an integer or a string. It's a noun. You can pass a function as an argument into another function.
Wow.
You can have a function that computes some logic and returns a brand new function as its result. You can literally store a dozen functions inside a list.
And that's where we get lambdas,
Yeah.
right?
Yeah.
Anonymous functions. We don't even need to give a function a formal name to use it. We just write the mapping logic directly inside the parameter of another function call.
It's incredibly fluid.
It is, but it brings up a major mechanical question for me. If functions are just floating around as values, getting passed from place to place, how do they remember the data they're supposed to work on when they finally get executed?
That is the magic of closures.
Okay, closures.
Yeah, a closure is created when you define a higher order function, meaning a function that generates and returns another function. The closure is a reference to that return function, but critically, it traps its environment. Its state, the variable bindings that existed when it was actually created, they get locked in at runtime.
You know, the analogy that came to mind when I was trying to visualize this is a snow globe.
Oh, a snow globe.
Yeah, like a closure is like taking a snapshot of a room and sealing it in glass. You write a function and you pack it with the specific constants it needs in that exact moment. Let's say you're generating a tax calculator for a specific user. So you lock in their exact local tax rate and their user ID, and you seal the globe.
That's a great way to picture it. And because functions are values, you can pass that sealed snow globe anywhere in your program.
Right. It can travel through 10 different files. And whenever you finally decide to shake it, whenever you execute that function later on, the environment inside is completely pristine. The local variables it knew about when it was created are still there, perfectly preserved in memory.
The mechanism behind this is super fascinating. Normally, when a function finishes running, the computer's garbage collector sweeps in and clears all its local variables out of memory, right?
Yeah, to free up space.
Right. But with a closure, the garbage collector sees that the return function still needs those variables, so it just keeps that specific environment record alive in memory.
That's so smart.
And because functional programming enforces immutability, it's incredibly safe. You don't have to worry that someone else in the program found your snow globe and secretly changed the tax rate while you weren't looking. The data is locked.
Okay, so we have these predictable, sealed units of logic. We pass them around like values. But how do we scale this up? We don't have a master script dictating step 1, step 2, step 3 anymore.
You scale up through function composition. Scalfani uses the analogy of Lego blocks.
Yeah, the Legos.
Your pure functions are highly specialized, and they ignore outside state, which makes them perfect, reusable blocks. You just snap them together by making the output of one function the direct input of the next.
But if everything is just functions snapping together, how do we manage complex data? Like, in object-oriented programming, we have massive objects with dozens of properties. What's the functional equivalent?
Functional programming operates on this core principle that code is data. In a language like Lisp or Clojure, the definition of your functional logic is written using the exact same structure as the definition of your data. They are both expressed as lists.
And the notes refer to them as heterogeneous nested collections. It's basically lists inside of lists.
Exactly.
And because everything shares this underlying list structure, functional languages come with a built-in suite of extremely powerful list operations. We're talking about map, filter, and reduce.
And these operations are what replace your imperative loops dynamically. Let's look at how they work under the hood. Map takes a function and a list. It automatically iterates through the list, applies your function to every single item, and generates a new list of the transformed items.
Okay.
Filter takes a true or false condition function, it tests every item, and produces a new list containing only the items that actually passed the test. And reduce takes a list and a combining function, and it folds the list down into a single summary value, like a total sum.
So you just declare the pipeline, take this raw list of transactions, filter out the declined ones, map a currency conversion onto the rest, and reduce them into a final balance. No loop counters, no temporary holding variables. It reads like a plain English sentence.
It's highly expressive, and again, because the functions are pure, inherently thread-safe. If you have a massive data set, you can split that map operation across 16 different processor cores simultaneously.
Wait, really? Just like that?
Just like that. Since none of the cores are trying to mutate the same memory addresses, you never get race conditions. Concurrency becomes almost trivial.
But hold on, I need to look at the memory implications here. Because we established earlier that variables are immutable, right?
Right.
If I have a list of 10,000 user profiles and I want to update the email address of just one user, I can't mutate that record. I have to generate a brand new list of 10,000 profiles with that one change.
Yes, theoretically.
If we're constantly doing that every millisecond, how does the computer not run out of RAM instantly? This sounds like a memory leak nightmare.
It absolutely would be if functional compilers actually copied the entire list every single time. But they don't. They use a mechanism called structural sharing.
Structural sharing. Okay, how does that work?
Under the hood, these lists are represented as trees of memory pointers. When you create a new list with one updated item, the compiler doesn't copy the other 9,999 items. It just creates a new node for the changed item, and then points back to the exact same memory locations for the rest of the unchanged list.
Oh, so the new list and the old list are actually sharing like 99% of the same physical memory space.
Precisely. And this is only safe to do because of immutability.
Because no one can change the old data anyway.
Exactly. If data could be mutated, sharing memory pointers between different versions of a list would cause catastrophic bugs. But since a value can never change once it's set, multiple lists can safely point to the same memory addresses without ever stepping on each other's toes.
It's brilliant. I mean, that solves my RAM panic completely.
Yeah.
But even with structural sharing, the notes do mention there are still performance trade-offs.
There are, definitely. Generating those new structural nodes still takes more overhead than simply overwriting a byte in place like C does. Plus, functional languages often rely on dynamic typing where the system figures out variable types at runtime, and lazy evaluation.
Lazy evaluation, meaning expressions aren't calculated until their results are absolutely needed.
Right. Deferring the math until the last possible second. It saves processing power if the value is never actually used, but tracking all those deferred calculations definitely adds overhead. So if you're building a high-frequency training algorithm where literally every microsecond of execution speed matters, an imperative language directly manipulating memory is going to win.
But the reality is most of us aren't writing high-frequency trading bots,
Right.
The notes point out that for modern multi-tier applications, raw execution speed is rarely the main bottleneck anymore. It's usually database queries or network latency.
Yeah, the hardware is fast enough now that the slight performance hit of functional programming is easily outweighed by the benefits. Code that is highly readable, naturally concurrent, and trivially easy to unit test. That saves companies massive amounts of debugging time.
Which is huge.
And you don't have to be dogmatic about it either. Composite applications are the industry standard now. You write your complex, state-independent business logic in a functional style, and then you just drop down to an imperative language for the specific modules that require raw, bare metal performance.
You just use the right vehicle for the environment.
Exactly.
So let's bring these high-level concepts back down to earth and back to your immediate responsibilities for CS330 so you can go test these spaceship controls out for yourself.
Sounds good. Looking at the syllabus, Lab 8 on AST decoration was already due back on April 6th, so hopefully you've got that completely squared away.
Yeah, that's in the rearview mirror. Your next major target is Monday, April 13th. You have a functional programming reading assignment due before class. Make sure you've completed your perusal annotations. The syllabus really emphasizes active reading, so don't just passively scroll through the PDF.
Yeah, engage with it. Ask questions. Highlight the mental roadblocks.
Also due on Monday, April 13th, is Lab 9, which tackles type checking. We spent a lot of time today talking about the rigorous provable nature of functional programming.
Which is so important. And understanding how a compiler strictly checks and enforces data types is the actual mechanism that makes those mathematical proofs hold up.
Right, the two concepts are deeply intertwined. So get those annotations done and dive into Lab 9. And as you're sitting down to code this week, keep this massive paradigm shift in the back of your mind.
Yeah, give it some thought.
Now that you've seen how a purely mathematical immutable system operates, take a hard look at your imperative habits. The next time you write a standard for loop or mutate a state variable in C or Java, ask yourself, are you actually controlling the logic of your program, or is the hidden state secretly controlling you?